In this screencast, we are going to wrap up kind of the last part of Spectroscopy C chapter that pertains to proton NMR, and we are also going to work an example problem of how to figure out an unknown substance using the NMR spectroscopy and data from mass spec and IR. So let's talk about some more coupling constants for a moment. Protons that are on carbon-carbon double bonds often give really characteristic splitting patterns. And so we want to look at di-substituted double bonds, and you can end up with three different types of di-substituted double bonds. You can end up with geminal protons. Now I want you to notice here, geminal means they're on the same carbon of the double bond. And then we've already talked about cis, and then there's also trans. And so when these protons are different, each proton is going to split the NMR signal of the other so that the protons appear as doublets, right? So in the previous screencast, I mentioned coupling constants can give us info about the structure. And this is a really good example where the magnitude of the coupling constant for these doublets depends on the arrangement of hydrogen atoms. So when we look at this, we're looking at E and Z 3-chloropropanoic acid. Now we haven't talked about E and Z at the moment, and we'll get to that, but right now it's just kind of ignore it. But the big thing here is we are looking at trans and cis. And what you can see here, right, both of these protons exhibit doublets, right? But the coupling constant is larger when those are trans. So we can distinguish between these two molecules based on their coupling constants here. Now, let's look at maybe a more complex example, okay? When we have a double bond that is monosubstituted, basically what happens is there are three non-equivalent protons. So look, this is an example where we have a double bond. It's monosubstituted, so there's only one substituent here, and you've got 1, 2, 3 protons, and all of these are not equivalent because they're in different chemical environments, right? This one's closer to this group, this one's farther away, but still attached to the double bond, and so on and so forth. All these protons right here are coupled together, okay? And so a really good example is vinyl acetate, which is this molecule. And we see HA, which gives us a singlet there exactly like we would expect. But when we look at HD, HC, and HB, we see structures that look like this. So we want to talk about that splitting for just a moment. Let's start with HB. Okay, and so I'm looking at this fellow right there, that's HB. And what happens here is HD splits HB into a doublet. Okay, so we're also then looking at this signal pattern here, and that's the signal there. So we see the doublet that it's split in, but notice that these doublets are also split again, right? And that's because then HC splits the doublets well, that's not helpful. Okay, there we go. Doublet into another doublet. And let's say 2 doublets, which is what we see right there. This is called a doublet of doublets. Okay. Now, when we look at this, if you want to imagine this in another way, right, we are still looking at HB, which is shown here, right? It's split into the two peaks, and then it's split one more time, and there's our doublet of doublets. Notice that we also get a doublet of doublets for HC, and then we get a doublet of doublets for HD. Now, let's look at some other protons that we'll encounter in a proton NMR. For example, let's look at ethanol here. Ethanol has 3 distinct protons, and so we end up with 3 signals in our NMR. We look here, right? This is split by these 2 hydrogens, so that gives us a really nice triplet here. We come down here and we see that the HB signal is split only by the 3 hydrogens of the carbon, right, into a quartet, which is shown here. The adjacent OH proton does not split the signal, right, due to that HB. So, and then of course HC is a singlet because OH protons are not split by adjacent protons. Now, why is that? So protons on electronegative atoms rapidly exchange between molecules in the presence of trace amounts of acids or bases. So the CH2 group of ethanol never feels the presence of the OH proton because the OH proton is rapidly moving from one molecule to another. So that phenomenon also occurs with protons on nitrogen as well. So the take-home message here, right, is that, and I'm going to put it kind of down here, right, is that an OH proton does not split the NMR signal of adjacent protons and then the other kind of comment here is that the signal due to an OH proton is not split by adjacent protons. Okay. So let's also look at cyclohexane for a moment. If you remember, cyclohexane has 2 protons that are in different chemical environments because one is axial and then one is equatorial. Now, and cyclohexane conformers can interconvert by that ring flipping that we see here. Now, because ring flipping is very rapid, at room temperature, an NMR just records the average, right, of all the conformers that interconvert. So even though cyclohexane has 2 different types of hydrogens here, we only are going to see one in an NMR spectra. Now, let's talk about protons on a benzene ring really quickly. Benzene has 6 equivalent d-shielded protons and exhibits a range of peaks generally right around 7.27, okay? And I pointed over here, but right, remember, benzene doesn't have a substituent on it. So this would be your generic benzene. And all of these would be equivalent, right? And all of those would show up right around 7.27, okay? Monosubstituted benzenes here contain 5 d-shielded protons that are no longer equivalent, and so they appear in different places. And so, for example, right, if we have an ethyl group as the monosubstitution, then you would see it above 7. Here, if we have an aldehyde, we would see it right below 8. If you've got an ether, you see kind of a split peak like this. So it really depends on what the identity is of the group that's attached, where it appears. Now, they're all going to be between 6.5 and 8, and they're generally going to be kind of this mess of peaks because of the all the electrons and that extra generated field that we talked about on the previous screencasts. So, using the proton NMR spectra, determine the structure of an unknown compound X that has a molecular formula C4H8O2, let's say we get that from mass spectrometry, and contains a C double bond O absorption in its IR spectrum. So we're looking at this and we say, all right, we've got this information, and now let's analyze our spectra. The first thing that you need to do is you need to determine the number of different kinds of protons. So when we look at this, we need to look at the NMR signals, because the number of NMR signals equals the number of different types of protons. So, for example, we have 3 different types. We have 3 peaks here, and so that indicates we have 3 different types of protons. Now, they're already labeled A, B, and C, but the big thing that we have here is 3. Now, the next thing we need to do is we need to use the relative area, which is in a graph right here, to determine the number of hydrogen atoms that give rise to each signal. So when we look at this, we need to remember that this relative area here is a ratio. Now, here's the deal. If you add the protons here, where it's 3 plus 2 plus 3, and that equals 8, and we know C4H8O2, that tells us the number of hydrogens for each peak. And so for us, that's going to tell us, hey, look, right? When we come here and we look at HA, okay, HA has 3 hydrogens, okay? And so Then we go to HB, and that has 2 hydrogens. So that carbon has 2 hydrogens. And then we go to HC, and that carbon also has 3 hydrogens. Okay. Now, generally, if you have 3 equivalent hydrogens, not all the time, right? It's going to mean there's a CH3 group there. Generally, if you have 2 equivalent hydrogens, it indicates there's a CH2 group. Not all the time, right? But most of the time, that's what we're going to see. Now, then we need to use the other information. So let's come up here to 3. And so we need to look at splitting patterns. To determine what carbons are bonded to each other. So, because so let's start with A. A is a triplet. Right? So that means there needs to be 2 hydrogens next to wherever A is. Okay? So there needs to be 2 hydrogens on an adjacent carbon. Okay. Then when we come to B, right? That's a quartet, so that means there must be 3 hydrogens on an adjacent carbon. And then when we look at C, right, it's a singlet, so that means there's no hydrogen on adjacent carbons. Okay, so when we combine the information that we have here with A and B, and then we look here at A and B, right, where A is a CH3 group, we think, and B is a CH2 group, and then we come over here and we say, hey, look, A this thing could fit the pattern is that it's a CH3 group and then a CH2, right, where this is A, and then it also fits the pattern here where B would be next to a carbon with 3 hydrogens, and the integration says there's 2 hydrogens on that. So the information we've gotten thus far is a really good indicator that we have an ethyl group. Okay. Now, we also need to figure out what to do with this singlet here. Okay. Now, that singlet is going to be, it looks like, due to a CH3 group that's next to a carbon with no hydrogens. So that could be a carbonyl. We know a carbonyl is running around in there, right? We also know that that could be a, because there's 2 oxygens. So that could be an oxygen that it's next to, right? Or, and these 2 seem to be the most prevalent, or it could be a carbon that has 4 groups, and these are not other carbons. These 2 seem more likely given the fact that we know there's a carbonyl, so we know there's a double bond, and we know there's only going to be 4 carbons in this. So kind of the next step is to really start to kind of put these together and use our chemical shift data to complete the structure. Okay, so now we're going to come down here to 4, and we're going to use the chemical shift data. Okay, so we need to put structures together that would kind of preserve what we're talking about, like all the splitting. So what we want to do is we're going to come up with some combinations where we keep this ethyl by itself, and then we attach it to these groups. Now, when we talk about attaching it to these groups, we need to remember there's 2 oxygens. So, for example, if we were to come down and attach this directly to, say, the carbonyl, that wouldn't make sense because you would expect there to be an oxygen in between there, okay? And so that would look something like CH3C double bond O. We'd put an oxygen in there, and then we'd have CH2CH3, like that. Then, when you look at this right here, we would need a carbonyl on the other side of it, and then attach that. So that would look something along the lines of CH3 O, C double bond O, CH2CH3. Okay. Now, each of these still preserve all of the splitting. So that's always a great double check, is once you put your structure together, go back and make sure it still has the same splitting. Now, chemical shift information is what's really going to help us here. We have a really electronegative oxygen atom here and a really electronegative oxygen atom here. And so we need to decide, right, based on that really electronegative oxygen atom, we also have this peak here. That's going to be the most downfield. So that indicates, right, the chemical shift of the most downfield peak indicates that carbon is attached to an oxygen atom. So when we go back and we look at what C is, right, C is that CH3 group that's a singlet. So that indicates the CH3 group that's a singlet is next to the oxygen. Well, this is the CH3 next to the oxygen. This is an ethyl group next to the oxygen. So if this were the correct structure, you would have a triplet that would be the farthest downfield. So that information tells us that this is the correct structure for the molecule that gives this NMR. All right. We will practice this more in class. If you have any questions, please feel free to stop by my office.